The morning of April 19th, 1945. Northfield, Guam, Mariana Islands. Lieutenant Darrell Landau stood beside a Wright R-3350 engine that had been pulled from a B-29 just hours earlier. The cylinder heads were scored black from overheating. 2 exhaust valves had broken free and been ingested into the engine, punching holes through 3 pistons before the crew chief managed to shut it down. This was the 4th engine failure Landau had seen that week, the 11th that month. The Japanese weren't destroying these superfortresses. The engines were destroying themselves. Landau was 22 years old, fresh out of Yale's Aircraft Maintenance Officer School, assigned to the 19th Bomb Group's 28th Squadron as Assistant Engineering Officer. He'd arrived on Guam in February, barely 3 months ago, and he'd never actually seen a B-29 until the Jeep driver showed him Northfield for the first time. Now he was responsible for keeping them flying. The problem was that the engines had other plans. The Wright R-3350 duplex Cyclone was supposed to be a marvel of American engineering. 18 cylinders arranged in 2 rows, 54.9 litres of displacement, 2,200 horsepower per engine, 4 engines per bomber. The B-29 was designed to fly higher, faster, and farther than any bomber in history. 30,000 feet, 350 miles per hour, 3,200 miles of range. But those specifications meant nothing when your engines caught fire halfway to Japan. The math was brutal, and everyone at Northfield knew it. Between November 1944 and March 1945, the 20th Air Force had lost more B-29 seconds to mechanical failures than to Japanese fighters and anti-aircraft fire combined. Engine fires were so common that crews developed a grim routine. Watch the cylinder head temperature gauges. When the number 3 engine starts running hot, prepare to shut it down. When the cowl catches fire, activate the extinguisher system. When the extinguisher fails to put out the fire, prepare to bail out before the wing spar burns through and the wing separates from the fuselage. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem wasn't that Wright Aeronautical couldn't build good engines. The problem was that the R-3350 had been rushed into production before the design was mature. Development started in 1937. The first prototype ran successfully in 1939, but then Wright put the R-3350 on hold to focus on producing R-1820 and R-2600 engines for existing aircraft. They also spent enormous engineering resources on the R-2160, a 42-cylinder radial that was eventually cancelled. By the time Wright returned full attention to the R-3000, 350 inches, 1941, Pearl Harbor had been attacked and America was at war. The Army Air Forces needed heavy bombers to strike Japan. The B-17 Flying Fortress and B-24 Liberator didn't have the range. Boeing's new B-29 Superfortress design did, but only with the R-3000, 350 engines. Wright received contracts for over 30,000 engines before the design was fully proven. 3 different factories began production. Wright's plants in Woodridge, New Jersey and Lockland, Ohio, plus Chrysler's Dodge Chicago aircraft engine plant. The engines rolled off assembly lines faster than problems could be identified and corrected. By 1943, when the first B-29 seconds began flying, the R-3350 was temperamental at best. The rear cylinders, those farthest from the cooling airflow, ran dangerously hot. The clearance between cylinder baffles and the cowling was inadequate, restricting airflow. The carburetor had a poorly designed elbow entrance to the supercharger that created uneven fuel-air mixtures. Some cylinders ran rich, others ran lean. The lean ones overheated. The magnesium alloy crankcase, chosen to save weight, could burn at temperatures approaching 5,600 degrees Fahrenheit if a fire started, hot enough to burn through the wing's main spar in seconds. But the most insidious problem, the one that would cost the most lives, was the valves. Exhaust valves operated in a hostile environment. They opened and closed dozens of times per second, exposed to combustion gases exceeding 2,500 degrees. The valve stems had to slide smoothly through guides while maintaining a gas-tight seal. The valve heads had to seat perfectly against hardened steel seats to prevent blowback. Any failure meant hot exhaust gases escaping where they shouldn't, eroding metal, causing more failures. Wright engineers knew the R-3350 had valve problems before the first B-29 entered combat. They proposed switching from cast cylinder heads to forged heads, which would provide better cooling and higher durability. But American forging capacity in 1943 was insufficient. Every forge in the country was already working at maximum capacity, producing artillery shells, armor plates, and components for thousands of other military systems. Adding R-3350 cylinder heads to the production queue would have delayed other critical programs. The decision was made to proceed with cast cylinder heads and accept the consequences. Those consequences arrived over China, over the Pacific, over Japan. Engines swallowing their own valves, exhaust valves breaking free from their stems, intake valves burning through. The failure mode was almost always the same. A valve would stick in its guide, unable to open or close properly. The piston would strike the valve head on the next stroke, bending the valve or breaking it completely. Metal fragments would be ingested into the combustion chamber. Pistons would crack, cylinder walls would score. The engine would shake itself apart. The official procedure when an engine swallowed a valve was to shut it down immediately, feather the propeller, and pray the damage wasn't catastrophic. B-29 seconds could theoretically fly on 3 engines, but only under ideal conditions. During takeoff from tropical airfields, loaded with fuel and bombs, 3 engines were insufficient. Some aircraft never got off the ground. Others made it airborne but couldn't maintain altitude. Crews had seconds to decide whether to crash straight ahead or try to turn back. Second Lieutenant Eddie Allen was conducting a test flight of the second XB-29 prototype on February 18, 1943, when the No. 1 engine caught fire. Allen was Boeing's chief test pilot, one of the most experienced aviators in America. He'd flown hundreds of test flights. He knew the procedures. He shut down the burning engine, activated the fire suppression system, and turned back toward Boeing Field in Seattle. The fire didn't stop. It spread through the wing structure. Fuel lines melted, more fuel fed the flames. Allen's voice on the radio remained calm even as the fire consumed the wing. He was attempting an emergency landing when the left wing failed structurally. The XB-29 rolled inverted and crashed into a meatpacking plant, killing Allen's entire crew plus 20 workers on the ground. The investigation determined that the fire started when a valve failed in the Wright R-3350 engine. The subsequent investigation and the required fixes forced nearly 50,000 engineering and tooling changes on Wright and its subcontractors. The logistical nightmare of managing these changes delayed the B-29 program by months. But the changes were implemented, production continued, and B-29 seconds began deploying to combat theaters in mid-1944 with engines that everyone knew still had problems. General Curtis LeMay took command of the 20th Air Force's XXI Bomber Command on Guam in January 1945. He was 38 years old, a hard-scrabble kid who'd worked his way through engineering. School, joined the Army Air Corps in 1928, and spent 16 years learning how to destroy things from the air. In Europe, flying B-17 seconds over Germany, LeMay had developed precision bombing tactics that maximized damage while minimizing losses. His combat box formations and pattern bombing techniques became standard doctrine. Now, standing on Guam, watching B-29 seconds take off for missions against Japan, LeMay recognized that European tactics wouldn't work here. The problems were different, the weather was worse, the distances were greater, and the engines were unreliable in ways that no amount of formation flying could fix. His predecessor, Brigadier General Haywood Hansell, had been fired after just 44 days because high-altitude precision bombing wasn't working. Only 5% of bombs dropped from altitude were hitting near their targets. Japanese weather, violent jet stream winds, and continuing engine problems made high-altitude operations a failure. LeMay's solution was radical: Stop flying at 30,000 feet where the jet stream scattered bombs and engines struggled for oxygen. Start flying at 5,000 to 9,000 feet where accuracy improved and engines ran cooler. Stop flying in daylight when Japanese fighters could intercept. Start flying at night when air defenses are less effective. Stop loading aircraft with defensive guns that added weight. Strip everything except tail guns and load the bombers with incendiary bombs instead. The first test of LeMay's new tactics came on March 9, 1945. 334 B-29 seconds took off from bases on Guam, Tinian, and Saipan, headed for Tokyo. They carried no bombs intended to destroy factories or military installations. They carried incendiaries, magnesium clusters, napalm, white phosphorus. The goal wasn't precision. The goal was fire. 16 square miles of Tokyo burned. Over 100,000 civilians died. It was the single most destructive air raid in human history. But the engines still failed. Flying lower helped with cooling during cruise, but takeoff was the killer. Guam's airfields were built on coral, exposed to tropical heat. Ambient temperatures reached 90 degrees. B-29 seconds taking off at maximum gross weight, 70 tons of aircraft, fuel, and bombs, required full power from all 4 engines for minutes at a time. Cylinder head temperatures soared past safe limits. Pilots learned to delay magneto checks until the takeoff roll itself, because running engines at high power while stationary for the traditional pre-flight check would overheat them. They used as much runway as possible, building up speed to increase cooling airflow before rotating. They climbed slowly, deliberately, monitoring temperature gauges like hawks. Despite these procedures, engines failed. Some caught fire on takeoff, others made it to Japan and failed over the target. A few lasted until the return flight and quit with Guam in sight, but fuel was exhausted. The pyramid of wrecked R-3,350 engines beside Northfield grew larger every week. One maintenance officer estimated that a mountain of junked engines represented 1,000 tons of failed American engineering. Lieutenant Darrell Landau walked that pile of destroyed engines in April 1945, taking notes. He was an engineering officer, not a mechanic. His job was to coordinate maintenance, manage parts inventory, and ensure aircraft were mission-ready. But Landau had a mechanical engineering background from Kansas State before the war interrupted his education. He understood metallurgy, thermodynamics, and stress analysis. He looked at failed components and saw patterns. The valve failures bothered him most. Landau pulled service records and compared failure rates across different aircraft. He noticed that some B-29 seconds were more reliable than others, not by much, but enough to be statistically significant. Same engines, same maintenance procedures, same missions. But some aircraft went months between valve failures while others failed every few missions. That shouldn't happen if the problem was fundamental design flaws. Design flaws affected all engines equally. Variable failure rates suggested operational differences. Landau started interviewing flight engineers. How are you managing the mixtures? What cylinder head temperatures are you seeing? What power settings are you using during climb? The answers varied wildly. Some engineers ran rich mixtures because they'd been taught that rich meant cool. Some ran lean because they'd been taught that lean meant efficiency. Some watched temperature gauges obsessively. Others barely glanced at them. Nobody had consistent procedures because nobody understood exactly what was causing the valves to fail. The official explanation from Wright Aeronautical was inadequate cooling. The solution they proposed was fuel injection to replace the carburetors, ensuring better fuel distribution and more even combustion temperatures. That sounded reasonable. Fuel injection would fix the mixture inconsistencies. But converting thousands of engines from carburetors to fuel injection would take months. It would require pulling engines, shipping them to depots, rebuilding them, and reinstalling them. The 20th Air Force couldn't afford months. The war wouldn't wait. Landau decided to figure out the problem himself. He pulled a failed engine, one that had swallowed valves on a mission to Osaka. He disassembled the valve train, examining each component under magnification. The valve stems showed a peculiar pattern of discoloration and scoring. The damage wasn't uniform. It was concentrated near the top of the stem, where the stem passed through the valve guide. Valve guides are simple components. A cylindrical sleeve pressed into the cylinder head, providing a bearing surface for the valve stem to slide through. The guides need lubrication, provided by engine oil pumped through passages in the priver, cylinder head. Without lubrication, friction increases. Friction generates heat. Heat causes the valve stem to expand. An expanded stem binds in the guide. A bound valve stops moving. A stopped valve gets struck by the piston. Landau requested the technical manual for the R3350. The manual specified oil flow rates, pressures, temperatures, but it didn't specify valve guide lubrication adequacy under all operating conditions. The engineers at Wright had designed the oiling system for standard power settings, standard temperatures, standard operations. They hadn't designed it for B-29 seconds, taking off from 90-degree tropical airfields at maximum gross weight, running at maximum power for extended periods, with cylinder head temperatures exceeding 230 degrees Celsius. Under those extreme conditions, the oil reaching the valve guides was too hot. Hot oil has lower viscosity. Lower viscosity means thinner oil films. Thinner films provide less lubrication. Less lubrication means more friction. More friction means higher temperatures. Higher temperatures mean even hotter oil. It was a feedback loop that ended with seized valves and destroyed engines. Landau had found the mechanism. Now, he needed a solution. The obvious fix would be improved cooling, but that required redesigning the entire cowling and baffling system, another months-long modification program the Air Force couldn't afford. Better oil couldn't help because military spec engine oil was already the best available. Higher oil pressure might work, but modifying oil pumps would require more time than available. Then Landau remembered something from his engineering classes at Kansas State. Valve stems in automotive engines were sometimes coated with special materials to reduce friction: chrome plating, phosphate coatings, anything that provided a low-friction interface between stem and guide. The R3350 valves were bare steel. Could coating them help? The problem was that coating valve stems wasn't something field mechanics could do. It required specialized equipment, chemical processes, and quality control. Landau couldn't coat thousands of valves on Guam, but he could try something simpler. He could change the fuel mixture to run cooler during the critical phases when valve temperatures peaked. Running leaner reduced combustion temperatures but increased the risk of detonation, which would destroy pistons and cylinder heads. Running richer lowered temperatures but wasted fuel and reduced power. The solution wasn't a single mixture setting. It has different settings for different phases of operation, carefully calibrated to keep valve temperatures within safe limits while maintaining necessary power. Landau drafted a new operating procedure. During ground operations and taxi, run slightly lean to minimize plug fouling. During takeoff, run rich to keep cylinder heads cool despite maximum power. During climb, lean out progressively as altitude increases and cooling airflow improves. During cruise, run at optimal mixture for fuel economy. During combat maneuvers, enrich slightly for power. During descent, lean out to prevent plug fouling from reduced power settings. The procedure required flight engineers to actively manage mixture controls throughout the flight, instead of setting one mixture and leaving it. That was more work, more vigilance, more opportunities for error. But it would keep valve temperatures under control. Landau briefed his idea to Captain Charles Keogh, the 28th Squadron engineering officer. Keogh was skeptical. Wright Aeronautical employed thousands of engineers. If this mixture management technique worked, wouldn't they have already figured it out? Landau's response was simple. Wright's engineers designed for ideal conditions. We're operating in conditions they never imagined. Keogh authorized a test. 1 B-29, 1 mission, 1 flight engineer briefed on Landau's procedure. The aircraft was number 42 to 93967, City of Lansford, a 19,000-pound bomb capacity B-29 that had already flown 23 missions. The flight engineer was Technical Sergeant William Morrison, one of the most experienced engineers in the squadron. Morrison had logged over 500 hours in B-29 seconds. He knew the engines intimately. He knew when they were happy and when they were about to fail. The mission was a night incendiary raid on Kawasaki, an industrial city south of Tokyo. Takeoff was scheduled for April 23rd at 2100 hours. Landau met Morrison at the aircraft 4 hours before mission time. He walked Morrison through the new mixture procedure, explaining the theory behind each setting. Morrison took notes, asked questions, and finally nodded. "I understand the idea. Let's see if it works." At 2100 hours, City of Lansford rolled onto Northfield's runway. 4 Wright R-3350 engines throttled up to full power. Morrison managed the mixtures exactly as Landau specified. Rich for takeoff, cylinder head temperatures climbed but stayed within acceptable limits. The bomber accelerated, lifted off, and climbed into the tropical night. Morrison leaned the mixtures progressively as altitude increased, watching temperatures, adjusting constantly. 7 hours later, the City of Lansford returned to Guam. All 4 engines are running normally. Cylinder head temperatures had peaked during takeoff, but never exceeded safe limits. No unusual vibrations. No warning lights. No smoke from the cowlings. Morrison's mission debrief was succinct. "The procedure works. The engines ran cooler than any mission I've flown." Landau didn't celebrate. One successful mission proved nothing. Engines failed randomly. Morrison might have gotten lucky. Over the next 2 weeks, Landau briefed 6 more flight engineers on the mixture management procedure. 6 more missions were flown with active mixture control. 6 more successful returns with all engines healthy. The pattern became undeniable. Aircraft using Landau's procedure had dramatically lower cylinder head temperatures and 0 valve failures. Aircraft using standard procedures continued experiencing problems. Word spread through the 19th Bomb Group. Other squadron engineering officers started asking questions. "What's this mixture technique your flight engineers are using? Can we try it?" By early May, more than 40 B-29 seconds in the 19th Bomb Group were operating under Landau's procedures. The group's engine failure rate dropped by nearly 60%. Missions that would have been aborted due to engine problems were completed successfully. The 20th Air Force's maintenance officers noticed the change. Engines from the 19th Bomb Group were lasting longer between failures. When they did fail, the failures were from normal wear, not catastrophic valve seizures. Colonel John Roberts, commander of the 19th Bomb Group, requested a meeting with Landau. Roberts was a veteran who'd flown B-17 seconds out of Australia in early 1942, back when the Philippines fell and the Japanese seemed unstoppable. He'd seen enough innovation under pressure to recognize real solutions versus wishful thinking. He asked Landau one question: can this procedure be standardized and taught to every flight engineer in the 20th Air Force? Landau's answer was carefully considered. The procedure works, but it requires skilled flight engineers who understand engine operation. We can't just publish a manual and expect everyone to implement it correctly. We need a training program. We need instructor flight engineers. We need buy-in from Wright Aeronautical so they don't countermand our procedures. Roberts understood bureaucracy. He'd spent enough years in the military to know that unofficial field modifications, even successful ones, were frequently shut down by higher headquarters who didn't like mechanics freelancing on expensive equipment. But Roberts also understood combat, effectiveness. His group was flying more missions with fewer aborts. That mattered more than procedure manuals written in New Jersey. He drafted a report to 20th Air Force headquarters, describing the mixture management procedure and its results. He didn't credit Landau by name. Individual lieutenants didn't get mentioned in official reports. But he made the case that this technique could be implemented fleet-wide if endorsed by higher authority. The report went to Major General Curtis LeMay's desk on May 14, 1945. LeMay read it, called his operations officer, and asked one question: does this actually work, or is this wishful thinking from one group trying to look good? The operations officer checked maintenance logs, compared failure rates, and interviewed flight engineers. His conclusion, after 3 days of analysis, was unambiguous. The 19th Bomb Group's procedure demonstrably reduces engine failures. It should be adopted across all B-29 units immediately. But LeMay was cautious. He'd been court-martialed twice as a junior officer for unauthorized modifications to aircraft systems. Both times he'd been vindicated because his modifications improved safety and effectiveness. But he'd learned that even good ideas could get you fired if you bypassed proper channels. He needed authorization from Wright Aeronautical before implementing widespread changes to engine operating procedures. On May 20th, LeMay's headquarters sent a priority message to Wright Aeronautical's Military Liaison Office. The message described the mixture management procedure, provided data on failure rate reductions, and requested technical assessment and approval for fleet-wide implementation. The response arrived on May 27th. Wright's engineers had reviewed the procedure. They agreed it would reduce valve temperatures. They agreed it would extend valve life, but they also stated that this level of active mixture management exceeded the skill level expected of average flight engineers. The procedure could work if implemented by experienced personnel, but poor implementation could make things worse. Wright's official position was neutral. They wouldn't endorse the procedure as mandatory, but they wouldn't prohibit it either. Individual bomb groups could implement it at their commander's discretion, accepting responsibility for any problems that arose. That was good enough for LeMay. On June 1st, he issued a technical directive to all 20th Air Force B-29 units. The directive described the mixture management procedure developed by the 19th Bomb Group. It specified training requirements for flight engineers. It mandated monitoring of cylinder head temperatures and documentation of results. It made adoption voluntary but strongly encouraged. Within 2 weeks, every bomb group in the Marianas was training flight engineers on the new procedure. By late June, most B-29 seconds were operating under Landau's system. Engine failure rates dropped across the entire 20th Air Force. The mountain of wrecked engines beside North Field stopped growing quite so fast. More missions were completed successfully. Fewer crews died in fiery crashes caused by engine failures. Landau didn't receive a medal. The Army didn't give decorations for maintenance innovations. He was promoted to first lieutenant in June, a normal career progression that would have happened anyway. His contribution was noted in his personnel file, a single line stating that he developed improved engine operating procedures. Years later, that notation would help him get engineering jobs in the aerospace industry. But in the moment, standing beside B-29 seconds that came home with all engines intact, watching crews who'd survived another mission, Landau's reward was knowing he'd saved lives. The story of the Wright R3000, 350, and the B-29 Superfortress is ultimately a story about the gap between design and reality. Wright's engineers designed an excellent engine. On paper, they calculated power outputs, cooling requirements, and reliability targets based on laboratory conditions and test cell operations. But laboratories don't have 90-degree tropical heat. Test cells don't require engines to run at full power while hauling 70 tons of bomber off a coral runway. Real-world conditions broke assumptions that seemed reasonable in New Jersey. The bombers themselves were technological marvels. Pressurized cabins, remote-controlled gun turrets, computerized fire control systems, radar bombing capability. The B-29 was the most advanced aircraft of its era, the ancestor of every strategic bomber that followed. But all that sophistication meant nothing when engines failed and crews died. The simple solution, the unsexy fix, was what mattered. Not fuel injection, not redesigned cowlings, not forged cylinder heads, just smarter mixture management, applied by flight engineers who understood their engines. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The improvement didn't come from factories or laboratories. It came from a 22-year-old lieutenant standing in the tropical sun on Guam, looking at failed engines and asking why. It came from flight engineers willing to try new procedures, even though they'd been trained differently. It came from a group commander willing to risk his career endorsing an unauthorized field modification. It came from a general willing to listen to ideas from lieutenants and flight sergeants instead of waiting for official solutions. By July 1945, the B-29's engine crisis had eased significantly. Failure rates were still higher than anyone wanted, but they'd dropped from catastrophic to merely concerning. Crews still watched temperature gauges nervously during takeoff. Mechanics still pulled engines regularly for maintenance. But the rate of catastrophic valve failures, the kind that destroyed engines mid-mission and killed crews, had decreased dramatically. Then came Tinian Island, August 6, 1945. A B-29 named Enola Gay lifted off, carrying a weapon unlike any used before. The engines had been specially selected, hand-built by development engineers rather than taken from production lines. The flight engineers had been trained extensively. The mission was too important to risk engine failure. The atomic bomb dropped on Hiroshima killed tens of thousands instantly. 3 days later, another B-29, named Boxcar, dropped a second atomic bomb on Nagasaki. Japan surrendered on August 15th. The war was over. B-29 seconds that had flown combat missions against Japan were gradually returned to the United States. Some were stored in the desert, some were scrapped. A few were retained for the new United States Air Force, which became a separate service in 1947. The lessons learned in the Marianas shaped post-war aviation: better engine testing protocols, more realistic operating condition simulations, field feedback loops that allowed combat modifications to be rapidly evaluated and implemented. Wright continued producing the R-3350 after the war. The engine-powered civilian aircraft, including the Lockheed Constellation and Douglas DC-7, post-war versions incorporated fuel injection, improved cooling, and all the fixes that couldn't be implemented quickly enough during wartime. Time between overhauls increased from 100 hours in early 1944 to 400 hours by war's end. Post-war civilian engines achieved 3,500 hours between overhauls. The R-3350 eventually became one of the most reliable large radial engines ever built, but it took years to reach that maturity. Lieutenant Darrell Landau returned to the United States in early 1946. He'd been frozen in place by General MacArthur's orders, requiring engineering officers to remain on station until replacements arrived. By the time he got home, he'd missed the fall 1945 semester at Kansas State. He re-enrolled in January 1946, finished his mechanical engineering degree, and went to work for North American Aviation, which later became part of Rockwell. He spent 37 years in the aerospace industry, retiring in 1992. He rarely talked about his wartime service, even with family. In 1992, Boeing held a 50th anniversary celebration of the B-29 Seattle. Landau attended and reconnected with veterans he hadn't seen in 47 years. Other engineering officers, flight engineers, and pilots who'd served in the 19th Bomb Group. They talked about missions, about engines, about the men who didn't make it home. Someone asked Landau about his mixture management procedure. He explained the theory, the testing, the implementation. One of the flight engineers, now in his 70s, said simply, "That procedure saved my life on at least 2 missions. I knew I could keep the engines running no matter what because I had control over the temperatures." Landau wrote his own history of the 19th Bomb Group in the 1990s, compiling stories from veterans, mission records, and his own memories. In one section, he described his discovery of the valve lubrication problem and the development of the mixture management solution. He was careful to credit the flight engineers who implemented the procedure, the mechanics who maintained the aircraft, and the commanders who endorsed unofficial modifications. He didn't claim sole credit because he understood that solutions in war come from collective effort, not individual brilliance. But buried in his account was a statement that revealed his thinking. He wrote, "If someone had only found and implemented this solution earlier, there would have been no need for the costly conversion to fuel injection, the tremendous turnover in engines, and the lost operation effectiveness. If this one malfunction and its simple solution had been implemented early, it could perhaps have shortened the war by many weeks." That statement, written 50 years after the fact, captures both the triumph and the tragedy. The triumph was that the solution worked when implemented. The tragedy was how many died before anyone figured it out. How many crews were lost to engine fires that better procedures might have prevented. How many missions were aborted. How many targets weren't struck because aircraft couldn't maintain their engines. Military history tends to focus on generals, strategies, battles won and lost. We remember Curtis LeMay for the firebombing campaign, for his ruthless effectiveness, for his willingness to burn cities to end the war. We remember the Enola Gay and its terrible cargo. We remember the mushroom clouds over Hiroshima and Nagasaki. Those are important stories, but they're incomplete. Behind every strategic bombing mission were thousands of people making sure bombers could fly. Mechanics who pulled engines in tropical heat, supply officers who requisitioned spare parts, engineering officers who analyzed failures and developed solutions, flight engineers who managed complex aircraft systems while exhausted and afraid. The war wasn't won by weapons alone. It was won by the unglamorous work of keeping weapons functioning. The B-29 could have been the most advanced bomber in history and still failed if its engines didn't work. The atomic bomb could have been the ultimate weapon and still been useless if the bomber carrying it couldn't reach Japan. Every piece of high technology depends on basic reliability. Every sophisticated system requires simple things to work correctly. Oil must reach valve guides, valves must slide smoothly, cylinder heads must stay within temperature limits. Lieutenant Darrell Landau understood this. He didn't try to redesign the R-3350. He didn't propose revolutionary modifications or dramatic engineering changes. He simply figured out how to operate the engines they had in the conditions they faced. He developed procedures that kept temperatures safe. He trained people to implement those procedures correctly. He saved lives by solving a simple problem that had been killing people because nobody had taken the time to understand it. The Wright R-3350 is remembered, if it's remembered at all, as the troubled engine that powered the B-29. The engine that caught fire too often, swallowed valves too frequently, and killed too many crews. That reputation is partially deserved. The engine had real problems. But the engine also powered every B-29 mission against Japan. It carried atomic bombs to Hiroshima and Nagasaki. It survived long enough for engineers to fix its flaws. It became the foundation for reliable post-war engines that powered civilian airliners for decades. The story of how that troubled engine was made functional enough to win a war is less dramatic than stories of air combat and strategic bombing. There are no dogfights, no flak bursts, no dramatic last-second bomb releases. Just a young lieutenant taking notes beside a pile of failed engines, asking questions, testing theories, and finding answers. Just flight engineers adjusting mixture controls, monitoring gauges, and keeping aircraft flying. Just mechanics pulling cylinders, replacing valves, and putting everything back together so crews could fly another mission. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.